Thank you for joining me again for the second problem of the Level 3 torque calculation series. This is question number 8, which is asking us to calculate the mass of block B so that the lever remains balanced. So again, remember on these balance problems, the key thing here is that the net torque, which is if you add up all the torques together, the positives and the negatives are going to subtract from the positives, so on, that if it's balanced, then it has to be 0. And that's equal to the two torques we're going to have in this problem. Okay, so let's just take a look and just bring this in. We have a lever that is equal distance on both sides. We notice here that they number it from 0. So 0 is not the middle. 50 centimeters is the middle, so we're going to have to think about that. And it's going to 100. And we have two masses, and we're going to assume that because we're dealing with mass in this case, that there's gravity that's going to be pulling down on both of them. And they're both going to be a force, gravity, which is what's going to be contributing to the torque. And we have a distance for each one. Now, I think it might be good to just mark up what our distances are. So I'm going to get my handy dandy ruler, and I'm just going to get a line going across from here to there. And we got our first distance going from the fulcrum to the mass, and then we'll do another one from here to there, and that is going to be our second distance. And while we're at it, because we've been doing a lot of torque problems, it's probably best that we just label what these distances are. So if I started from 0 to 50, that's going to be distance for A, and that's going to be equal to 50 centimeters. And from 50 to 75 is going to be the distance for B. That's going to be equal to 25 centimeters. All right, so we can see my forces, I can see my distances. Now I just need to start calculating what these are so that I can get the answer. So we're going to start with our mass. Whenever they give you the mass to begin with, be prepared. You're going to have to use Newton's second law, which is that force, in this case, we're going to be dealing with gravity, is equal to the mass times acceleration of gravity, which is 9.81 meters per second squared. And they gave us a mass, and we already know the 9.81, so we can just plug and chug this. I have 10 kilograms times 9.81 meters per second squared, and that is equal to 98.1. I like when they give me nice numbers. Newtons. And I'm going to double underline this because we're going to need this for a little later. Just being consistent with my red gravity color. Okay, so I know my force of gravity, and in these problems, typically we've been getting some 90-degree angles, so that's great. We don't need to worry about the sine theta, and if we did, it would be 90 degrees, and it would equal 1, and it wouldn't change what our result is. So we're going to calculate our torque now. So the torque acting on the lever from A is equal to the force of gravity coming from it, which is our 98.1 newtons, times the distance, times the distance, which is in centimeters. Now, here's the deal. We could just plug in 50 centimeters and it won't give us any issues, but you did have some metric prefixes or metric conversion quizzes, so we might as well just utilize that skill. I'm going from centimeters to meters, so I'm going up, which means that I have to move my decimal place to the left, and it's 2 hops. 1, 2, and so I get 0.50 meters. So I can plug in 0.50 meters, and now I can plug and chug out an answer. So I have 98.1 times 0.5, and I get 49.05 Newton meters. Okay. What this means, since we're trying to balance it, is that the torque of block B, oh, you know what, the block B has to be equal to the torque of block A, but it's just going to have a sign difference. So let's see, if this one's going counterclockwise, that's positive. So we would end up having a negative torque for B, but we can leave that out. We just know it needs to equal 49.05. So let's get to it. I know that torque of B has to equal 49.05 Newton meters, and I'm just going to put here that it's a negative you wanted to. And I know that the torque of B is equal to the force of gravity for B times acceleration of gravity. Oh, sorry. No, not times acceleration of gravity. Sorry, I was getting in a little autopilot. Times the distance for this one. And while we're at it, we might as well do this conversion. 2 decimal places again to the left, so it's 0.25 meters. So now we can plug and chug. Or not plug and chug, we're going to do a little bit of arranging our equation. I'm going to divide both sides by the distance, since I need the force of gravity to find the mass.
Yeah, I know she is an SUV. I don't think it's forward drive.
All right. So now we can plug and chug. I have my 49.05 Newton meters divided by my 0.25 meters, and it gives me a force of gravity, 49.05 divided by 0.25, and I get that, oh, that seems good. I get a force of gravity of 196.2 newtons. Just about finished. It wanted the mass, not the force of gravity, but just like the previous problem, we can do that conversion. Force of gravity divided by acceleration of gravity would equal the mass. So that's 196.2 newtons divided by 9.81 meters per second squared. And what do we get? We get 20. And we're going to reflect on that for a little bit just to make sure it's reasonable. I get 20, and this would be kilograms. And let's take a look. Mass A is 10 kilograms. B we don't know. But mass A is 50 centimeters and B is 25. So if mass A is twice as far than mass B, then I would need half as much mass as B. Or if B is half as far, then it needs twice as much mass. So this is great. Yeah, 20 is twice as much as 10. And there you have it. Thank you very much for your time and have a great day.